Now, solving exponential equations. So there's several ways to solve exponential equations. And we're going to talk about two methods. There's some other methods that involve complicated properties of logarithms that we're going to avoid. All right, so we're going to keep this kind of simple. The first method is to solve equations with the same bases. So what that means is here I have an expression 2 to the 4x minus 2. And I got this number 64. Well, 64, if we do a prime factorization, we can break it into a whole bunch of 2's and a whole bunch of 2's. Now you may know that it's just it is a power of 2. Well, how many 2's do we need? 2 to the first, 2 to the second, third, fourth, fifth, sixth. So 64 is 2 to the sixth. So if we can write this side as a power of 2, and this side already is a power of 2, then that means these two powers must be the same. Does that make sense? So 4x minus 2 must be equal to 6. And now that's a pretty easy equation that we can solve. It's just a linear equation, right? So 4x equals 8. Divide both sides by 4. X equals 2. All right, so we can rewrite both sides as a power of 2. Then set the exponents equal to each other. That's all we're doing here. And then it's a simple equation to solve. Well, how about this? We got 25 to the y. Well, 625 is not 25 squared or anything like that. If you square 25, you're going to get a number bigger than 625. But you may notice that 625 is a power of 5. It is 5 to the third power. And 25 is 5 to the second power. And if we clean this up a little bit more, 5 to the second to the y is 5 to the 2y. And this is 5 to the third. Now we've rewritten both of these using bases of 5. Since the bases are the same, the exponents have to be the same. So that 2y has to be equal to 3. And if we divide both sides by 2, then we see that y is 3/2. Okay? So again, the key is to write both sides with the same base. Here we have a base of 9. Here we have a base of 27. Now 27 is a power, not a power of 9. 27 is a power of 3, right? This is 3 to the third power. And we notice that 9 is 3 to the second power. So I'm going to rewrite that 9 as 3 to the second. And I'll bring my x plus 3. So we're just rewriting it, but now we've got a common base. So you got to kind of recognize some things about the bases here. Okay? So now we're going to multiply these powers. So power to power, we multiply. So that's going to be 2 times x plus 3. And we can clean that up a little bit, right? That's going to be, we'll distribute this, 2x plus 6. And now we have our bases the same. And our powers have to be equal since we got a power of 3 and a power of 3. So now we can just rewrite that as 2x plus 6 equals 3. And it's all downhill from there, right? 2x equals negative 3. Divide by 2. And x is negative 3/2. That's how we do it. Now, sometimes we can't easily write them as the same base. So we need another method, all right? So here we're going to solve an exponential using logarithms, all right? Now, this is a pretty simple method here. Again, if you go looking online, you're going to see some methods that are a little more complicated, but I'd recommend starting with this method, okay? Here's our steps. First thing we're going to do is we're going to get that exponential all by itself. So for this example, we're going to subtract 4 from both sides, and that leaves us 5 to the x plus 1 equals 26. All right. Now, what we're going to do is we're going to write an equivalent logarithmic equation. So we're going to change this to a logarithm. We're going to keep in mind this relationship that b to the y equals x. We'll swing that base around, and we can rewrite this as y equals log base b of x. Okay, so we can change these. These are equivalent equations. We can change an exponential equation into a logarithm. So let's try that here. Okay, so notice we have 5 to some power equals 26. So we're going to take that base. The base of the exponent becomes the base of the logarithm, and that gives us log base 5 of 26. And then we have x plus 1 is the exponent, or the power. All right, so this just represents a number, and in fact we don't care what that number is right now. It's a decimal number. We're going to find it in a few minutes. Okay, last thing we need to do is we need to go ahead and solve for the variable. So let's subtract 1 from both sides. Okay, now this is an irrational number. I don't know what that decimal is. So the best I can do right now is I can write this as log base 5 of 26 and minus 1. Now this is an exact answer. So when we want an exact answer, there it is. Because the log base 5 of 26 is an irrational number. It's a decimal number. And so this is exact. Now if we want an approximation, we can go to our calculator and we can use our change of base. So in our calculator, we're going to, let's bring this on over here. So we want to change the base here. So we have, we're going to use natural log of 26. And we're going to divide that by the natural log of 5. Again, you got to make sure that the 5 doesn't get stuck in the parentheses there, okay? Let's make this a little larger so you can read it. Okay. Okay, so this is our change of base formula. Okay, so the natural log of 26 over the natural log of 5, well, that is about 2.024 minus 1, which is 1.024. So there is a decimal approximation. All right, so again, what we're going to do is we're going to get that exponent by itself. We change it to the logarithm so the x is no longer in the exponent, and then finish it off. We're going to get an exact answer with a logarithm, and then we can use our calculator with our change of base. The 26 went up top, the 5 went down below here, and then we can get a decimal approximation using the change of base formula. And that's our method that we're going to use. Again, we're not going to use the method of taking the log of both sides. Okay, this is just using the definition, and it's pretty straightforward and simple. So let's practice that a few times here. Okay, here we want to solve this, so we want to get rid of that 3 first. We don't have the exponential all by itself. 4 to the x, that's our exponential. Now it's all by itself. So now we can change the base, or change it to a logarithm. We've got exponential by itself. Let's swing the base around. So we have log base 4 of 25, and that equals x. All right, so we just swing the base around, write it as a logarithm. Okay, and there's our exact answer right there. So we took the exponential equation, we changed it into its logarithmic form. Now if we want the decimal approximation, we go to our calculator, and we're going to have a natural log of 25 divided by the natural log of 4. And that's going to give us about 2.322 as our approximation. Okay, so again, get that exponential by itself first and change it into a logarithm. Okay, all right. How about this one? We want to get this exponential all by itself. There's our exponential, e to the 2x. E is a number, e is about 2.718. Okay, don't go just erasing it. This is not 10 times e. This is 10 times the power. Okay, our order of operations says exponents go first. So we've got to get that 4 out of there first. We're going to isolate that exponential. And that's going to be 30. Let's divide that 10 off because it's being multiplied. Okay, e to the 2x equals 3. So we've got to divide. Now we've got that exponential all by itself. Some number, which is e, 2.71828, to the 2x power. That's great. Now we can take the base, swing it around. We're going to change this into logarithmic form. So this is log base e of 3 equals the exponent 2x. Okay, so this is just saying e to the 2x power equals 3. That's what this means. Now we have a special way of writing the natural log, or log base e, that is the natural log of 3. So if we have base e, we go ahead and write that as ln. And we have one more step. This is 2 times x, so let's divide by 2. And that gives us our exact answer. Our exact answer is the natural log of 3 divided by 2. That's exact, because the natural log of 3 is a decimal number. Well, we're going to use that in just a second. We'll use our calculator. We can go plug this into our calculator now. And we get our approximate answer here. And that's going to be the natural log. The natural log of 3 divided by 2 is about 0.549. Okay? And you don't need to do any change of base here because our calculator has a natural log on it. Just punch the natural log of 3 divided by 2 and you'll get 0.549. Okay? All right, one more here. Again, we want to get that logarithm or that exponential all by itself. 10 to the x plus 2, that's the exponential. So let's get that 4 out of there. And we have 10 to the x plus 2. 28 divided by 4 is 7. Got our exponential all by itself here now. And that's a common log, so we don't usually put the 10 on it. We can just write it this way, log of 7. And now we can subtract 2 from both sides. Again, we want to keep this exact. Now don't go trying to, that's not 7 minus 2. Can't combine that because this is, if it helps, put parentheses. The 7 is in the log. So we have the log of 7 minus 2. You can't go combining these because this is not in the log. This is outside the log. It's kind of like being in a square root and not in a square root. So that's the exact answer. The log of 7 is a decimal number. Okay, so that's exact. We can find an approximate by going to our calculator and hitting the log button. Or if you're on Desmos, you can just type log, L-O-G. That's a nice thing about Desmos. If on a, you can just type. Or you can use the function key on Desmos. So the log of 7, that goes in the parentheses, and so you can close the parentheses and then subtract 2. And that gives us about negative 1.155. All right? There you go. So get that exponential by itself, then change it to a logarithm. If it's not a common log or log base 10, then use a change of base formula to get the decimal. All right? But make sure you get that exponential by itself first. That's very important. All right?